This is Elevate, a rocket that steers itself, and we are seconds away from its first ever launch.
At least, that's what I thought. This project turned out to be one of the most stressful, frustrating,
oh no,
yet rewarding projects I've ever done. And I barely got it done in time.
Well, I'll be damned. He did it.
2 years ago, I saw a video from BPS Space showing a rocket that could stabilize itself using thrust vector control. And like every engineer watching, I thought, how hard could it be? I tried this once before and it went badly. The flight computer was unreliable, the software was a mess, and the TVC mount was sloppy enough to make control basically impossible. So this time, I decided to fix everything. After many revisions, I came up with this. In the lower end sits the thrust vector mount, the device that directs the thrust of the ST's F-15 rocket motor to control the rocket. This time, I beefed up the push rods, used tighter tolerances, and printed using more rigid material to increase precision. Above it sits the avionics bay, which houses the new flight computer, Maverick. This is the brain behind the rocket. It also has a telemetry antenna, batteries, a camera, and a switch to arm the computer. On top of it is the parachute bay, which we pressurize using a black powder charge to eject the parachute. And this is all housed inside a 74mm cardboard airframe. Everyone knows that the cooler it looks, the better it performs, so after building the whole thing, I tossed it in a glossy black base and then used a paper stencil for the name. If you want to learn more about my flight computer or the build of the rocket itself, be sure to check out my previous videos on those in the description.
But I have a big problem. All of that was the easy part. The part I dread most, the part where the most can go wrong, that's in the software and simulation. And I only have 2 weeks to finish all of it while still studying for my final exams. This might be tight. So let's not waste any more time. There are 4 main problems I need to solve. 1, I need to know where we are. 2, I need to know where we want to go. 3, I need to know how we're going to get there. And 4, I need telemetry, or way for me to get data wirelessly from the rocket. To know where we want to go, we first need to know where we are and where we're pointing. One of my long-term goals is catching a rocket like SpaceX, so position is really important. That brings me to my next point, my secret. There's something I didn't tell you. The goal of Elevate isn't just to control itself. There's also a new position technology that I want to test that, to my knowledge, has never been used in this application before. Typically, GPS RTK is used for position, but there are 2 problems with this. 1, it's wicked expensive. $200 for a single module is just not something I'm willing to pay. And 2, it has an incredibly slow update rate.
This led me to ultra-wideband, which uses a pulse signal between the device and the ground station to calculate distance. With a few ground stations, you can then trilaterate position.
And get this, it has the same accuracy as GPS RTK, but it's over 10 times faster and 10 times cheaper.
It's usually used indoors for short-range location, but it should still work for my flight profile. I verified accuracy and then moved outside to test the max distance I could actually read. I was able to get up to 30 meters pretty consistently, which should be way more than enough. Still, I'll just use it passively for the first flight. However, we still need to know our orientation.
So for this, I decided to use a multiplicative extended Kalman filter, which is essentially just a fancy algorithm that allows us to fuse our sensor data to get a more accurate estimate of where we are and where we're pointing. Troubleshooting this sucked. It took at least 6 or 7 days by itself. It took an entire week to troubleshoot by itself. And the sheer amount of issues I ran into with my magnetometer solidified its place as my #1 least favorite sensor of all time. Just take a look at this test data. The left side is what I was getting, and the right side is what it should have been. As you can tell, it's not even close. But finally, I got it working.
Nice.
But this algorithm is too slow and unreliable during flight. So after ignition, we'll switch to just using the gyroscopes for a more responsive control loop. You might then ask, why not just use the gyroscopes in the first place? It's because the gyros only measure the change in orientation. If the computer doesn't know where it started, it has no idea which way is up. That's why I use the Kalman filter, so we can be sure our initial orientation is accurate no matter the conditions.
I also coded a state machine so we know what state of flight we're in. This handles when to send commands, when to fire the parachute, etc., etc. This is really important to get right, otherwise we'll end up with a crash landing like my first attempt. Yeah, no thanks.
I couldn't fit every line of code in this video, so if you want the deep dive, check out my Patreon. I'm also officially releasing the production files for Maverick, which is perfect if you're looking to jumpstart your next flight computer design. Supporting the channel can also get you access to STL files and early access to videos like these. Link in description.
Up. Where else would we go?
Say we're pitched over 5 degrees. What's the optimal correction to point up? How do we know the shortest rotation and how to direct the mount to get there? For this, I'll be using the same limited attitude controller described in one of my previous videos. If it ain't broke, don't fix it. The quick explanation is, we compare the current and desired orientation up, then find the shortest path between them and calculate where to point the motor to steer us there. This is arguably the most important software in the rocket, so we really need to make sure we get it right. But how do we know it'll work before we launch?
That's where simulation comes in. To verify and tune the control system, we'll first create a really accurate system model.
I began by taking some measurements, such as center of mass and mass moment of inertia. The mount itself is also incredibly important, so I characterized it for both sides.
Alright, we need to move fast here. I'm going to plug it in, hook it up to power, and we should see this oscillate back and forth, testing the frequency response of the servo motors. Did you see that? Oh my gosh. I have to hold it down.
Once this was done, I made a Simulink simulation to test how it performs. After testing with different gains, or the knobs that tell you how fast you actually want to correct, I found some that worked. Nice. If this is wrong, I might not get a second chance, so to really seal the deal, I performed Monte Carlo simulations while varying key parameters. In monkey terms, this is essentially just throwing a bunch of differently sized bananas from different angles at your machine to see how it responds. There's a great saying, all simulations are wrong, only some are useful. So I did my best to use a minimal amount of effort to get to real-world testing as quickly as possible. Once done, all I had to do was test it. I began with a GUI to visualize the data. This took ChatGPT, I mean me, a couple of tries, but overall it came out pretty great. On the right side is the current orientation of the rocket, and on the left side we have the sensor data and command buttons.
Wireless communication was much less simple. Honestly, it was so hard, I barely finished. Pause.
I got transmitting and receiving working, but as soon as I tried both, it all broke.
This is not good. My sensor filter isn't working, logging data isn't working, and I need this done in 3 days.
For some reason, the data packets were super inconsistent.
Not sure where this might be coming from. While coping through YouTube, I saw a video from Basically Homeless that gave me an idea.
Technically this would work, but would add a lot of weight and wouldn't be as precise. So I started thinking like a monkey, which usually works. 1 not strong enough, 3 stronger. 1 not strong enough, 3 stronger.
No received packet? Just transmit 3 times. Problem solved. You might say, hey Garrett, you have a settings issue, you have a timings issue, blah blah, shut. I have 3 days left. We just need it to work. We don't need perfection, we just need it to work.
Oh my gosh.
Yes, it's working. Oh my gosh. I'm testing out the RF communication between the ground station and the flight computer. This is finally working. This has taken so long just to get this. Look. You have no idea how long it took for this to work. Oh my gosh. This was so painful. I then took it outside and it worked beautifully until... Whoops. Luckily, nothing was broken, so I decided to also quickly test the ejection charges. And now for one of the most important parts, the camera. This is a Runcam Split 4K, and it's enabled using the flight computer. It saves data to this SD card in 1-minute increments, but if it doesn't get to the 1-minute mark and close a file, it's gone. Let me repeat that one more time. If it doesn't get to the 1-minute mark and close a file, it's gone. Gee, I hope that's not a problem later. I just realized we need a way to launch this, so let's build a launch mount. This thing needs to survive fire, heat, and my bad decision, so it needs to be thick. With 3 C's. My last launch mount was wood, but wood is so last century, so let's do something different. The platform is a 4mm stainless steel plate from JLC PCB. I used them previously for my first flight computer, but never their sheet metal service, so I honestly wasn't sure what to expect. But man, was I surprised. This thing is a beauty. The logo engraved in the center gives it such a nice look. I'm really happy with how it came out, and I would definitely use this service again in the future. JLC PCB also offers high-quality PCB, CNC, and 3D printing services, so definitely check them out in the description for your next project. Thank you so much JLC PCB for sponsoring this video.
The platform sits on these adjustable 3D printed legs, with the launch mount sitting in the center. On the front is a Spots Mount EVA, my previous flight computer which I'm now using to ignite the rocket motor.
Although I haven't actually used it since last year, it worked before, so no need to test again, right? Right?
Because of how frequently the rocket fell under any wind, I grew very concerned that the mount wasn't tight enough to prevent it. So I added some layers of tape on the inner edge.
Too little and it might fall over, but too much and it won't leave the pad. That would be bad. With everything complete, I performed a fully integrated test. Alright, so this is the setup. I got the ground station here, and I'm just going to be running up the stairs to simulate flight. Let's do it. Before heading out, let's define what success even means. For me, if the rocket stays vertical, deploys its parachute, and we get the data back, I'd call that a win. So let's do it. All right, we're headed over to the launch. Not gonna lie, I'm feeling a little nervous. Aid, what are your predictions?
I don't know anything about rockets, but I trust you and I trust your engineering. So I'm hoping for a successful launch.
Yeah, me too. I think I've done everything I can to make this a success. I'm a little bit worried about the wind, but I guess we'll have to see how it goes.
This is Aid, and he'll be helping me out. He also runs a YouTube channel with some really cool projects, like this robot dog. You should definitely check him out after this video.
We're back out here after nearly a year. It's freezing and it's super windy, but we're gonna try to send it, so let's do it.
We had to move fast because I knew it was gonna snow in just a few hours. I started with the pyro charge for the parachute, which was incredibly hard because of the wind and the fact it was so cold I couldn't stop shaking and I could barely move my fingers.
All right, there's our ejection charge.
I then added the motor, set up the launch mount, and finally, after all of this work, it was time for the moment of truth.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
And nothing. I figured it was a fluke, so I set the sequence and tried again. And nothing again. When I took out the charge, I noticed something weird. It hadn't even gone off. The fact that it refused to ignite told me the issue was with Eva. I knew I should have tested it beforehand. I took it inside and tried directly shorting the pyro channel, but still nothing. Something was seriously wrong. Not only that, but with every second I wasted, the snow was getting worse and worse. I wasn't just fighting the rocket, I was racing the weather. Eventually, I found the issue to be these resistors I used to limit current. For some reason, the resistance was over 70 times higher than normal, which meant they blocked anything from firing. Easy fix, right? I'll just solder over the junction. Wrong. Right as I began, I realized I forgot the cable for my iron. Desperately, I racked my head for a solution. Surely, there must be a way to save the day. And then I had an idea.
If connection no good and no can solder wire, then what if just tape wire? And now connection good. Yes.
Somehow, it worked. There was hope. Maybe this launch would work after all. We headed back into the storm, started the sequence, and held our breath.
Ready? Let's do this.
Even though the charge blew, the motor still did not ignite. At this point, I had just one more trick up my sleeve. You see, before I was using standard ST's igniters, which are known to be inconsistent. So just in case, I brought a few firework igniters that were much more powerful. One last shot. I saw a bright flash of light and still nothing. At this point, we were tired, wet, cold, and ran out of time. So we decided to pack up.
Honestly, the launch broke me. We're out there for hours and I don't think I've ever been colder in my entire life. I think the issue was a faulty motor, so we're gonna give it another shot with a fresh batch of motors and hopefully that fixes it. Because if not, I'm honestly not sure where to go from there. And there might not be another chance to launch until the winter's over, so we need to do this now. I also took this time to actually solder the wire to Eva to give it a better connection.
And actually tested it.
We're back here for attempt number 2. The weather is way nicer and the clock is ticking down, so let's get after it.
Yeah, you can start recording. Alright. I'm gonna try to get this as deep in there as possible. So
That's what he said.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Well, I'll be damned. He did it.
1.
Well, I'll be damned.
3, 2, 1.
I'll be damned.
Come on, parachute.
Yes!
Woo! Oh my gosh. Congrats. Oh my gosh.
Look at that!
That was so good. Oh my gosh. I don't think it could have been much better than that. Look at, there's no damage. Oh.
Let's go!
Let's go. Oh my gosh.
How do you feel?
I feel so good right now. Tipped a little bit off at the end,
Yeah.
but overall, I think that's a success.
Nice.
Should we try to launch it again, do you think?
Heck yeah.
Might as
I
well.
want to see more rockets, man.
All right.
I made a second charge, reintegrated the rocket, and we set it up again. While inserting the rocket, I noticed it was harder because of some mud from landing. No problem though, I thought. Surely it worked once, so it should be fine this time.
4, 3, 2, 1.
Oh no. What happened?
Damn it, it got stuck in the launch mount.
Oh no.
Fuck. Oh my gosh. That's pretty not ideal.
Well, the parachute deployed.
Barely too much friction. Like, I just pulled it off right now and it wasn't too bad. Oh,
Are you telling me that thrust
that.
couldn't overcome that friction?
I guess not.
Oof. The extra friction prevented the rocket from lifting off, until the legs of the mount literally melted away from the hot exhaust gases. It would have been such a simple fix, but the first launch still went great, so I'll take it.
At this point, I'm sure you're wondering, what happened to the onboard footage? Well, you remember what I said earlier?
But if it doesn't get to the 1 minute mark and close the file, it's gone. Hypothetically, theoretically, the camera may have stopped recording just soon enough for me to lose all of my precious launch footage. I have up to maybe 10 seconds before launch and then nothing.
Honestly, this hurt 10 times more than the rocket getting stuck, just because of how much I was looking forward to seeing this footage. But it's okay. I failed a lot while making this project, and it's definitely those mistakes that have taught me the most, as painful as they are. 2 years ago, I asked, how hard could it be? Turns out way harder than I imagined, but so worth it. Thank you for taking this journey with me. I hope you enjoyed. Stay tuned because I have some crazy projects in the pipeline. See ya!